Hello everybody, this is Mr. Smith. Today in chemistry we're going to talk about data, the measurements, measuring, how to measure, we're going to follow up with the units in terms of looking at the units that come out of the measurements, some of the calculations, specifically talking about density. So here is some lab equipment that you would find in most chemistry labs. We have a electronic balance to get the mass of things, a digital thermometer. We have graduate cylinders to measure volume, rulers to measure length, and analog thermometers to get the temperature without a digital thermometer. So we have kind of two realms of ways of, devices to measure things, of equipment. The digital realm is obviously a bit more modern. You can report those exactly as they appear on the digital scale. So whatever digital numbers are there are the numbers you can write down on a lab sheet. Now the analog takes a bit more work and effort. Not only do you not get a readout for it, you kind of have to guesstimate precisely what the value is. And beyond that, you have to be able to write down the correct number of numbers. And so for a digital, that's quite explicit, just write down what they give you. But when it's an analog, it takes a bit more thought process that we're going to talk about in this video. And so here are some analogs in terms of not being digitally sound. So we have some thermometers. This is from a protractor. This will be a ruler here. How far spaced out these lines are between the 20 and the 29, or in this case, between the 100 and the 99, that gives us permission to write down more or less numbers. It gives us really a mandate of how many numbers and how many digits we must write down. So here's a graduated cylinder. Graduated cylinders come in so many sizes that it takes a few slides to talk about how to read them. The biggest thing is read them at eye level in terms of experimental procedure. Read the bottom of this meniscus. You see this curve down here. What's the general topic is to read the bottom of that meniscus, how the water sticks to the sides of the glass. It gets pulled up a bit. By convention, we read the bottom of that curve, which we call a meniscus. But other than that, the line values are different depending on the size of the graduated cylinder. So that's going to take a little bit of practice. So you kind of read a graduated cylinder, kind of 3 steps. Always read the bottom of the meniscus, determine what value. So this takes a bit of a thought process. So you see the big bold 4 and a big bold 5, and there's quite a few lines in between that. So you almost have to guess and then check what each line does for you. So for this one, each line counts as a tenth. And so the value would be 4 and 5 tenths, or 4.5. And then beyond that, step 3, you can actually go one place further. Because that line, that meniscus is on that line, you can go one place further. So in this case, 4.50. There we can maybe think 449, 451. There's some estimation in that last digit. But the 4 is established by the big bold line, the 5 is established by the relatively thin line, and the 0 is an estimate. So the 20 of us, the 20 students in the classroom can look at this, and all of us would agree on 4. All of us would agree it would be about 50, perhaps 48, 49, 50, 51, 52, but some reasonable closeness to the 4.50, and all of those would be acceptable. So here's another one here. Again, with the different scale, the lines mean different things. And so now each line is not a tenth, but actually a whole number 1, because here's a 10, here's a 20. And now you have to kind of almost take a guess and check as to, is each one a tenth? Well, if I did that, 10 wouldn't become 20 in this amount of space. So each of these lines must mean 1. So again, I estimate we're 2 above 10, which is 12. Where the curve is right on the line, so that makes it 12.0. Again, some kind of estimation that's there. Here's another graduated cylinder. Again, kind of a different scale yet again. We go from 80 to 90 to 100. So each of these smaller lines are not a tenth or 100 or even a wholes place. Each of these count by 2. And again, you need to count by 2 to go from 80 to 100 with this many lines. 82, 84, 86, 88, 90, 92, 94, 96, 98, 100. So it's kind of an educated guess and then a check to make sure that it is correct. And so that meniscus is on that first line above the 80, so 82.0. Here's another one to try. So 10, and now you have to guess how much each line is worth. 10 to 15, that means each of these lines is 1. This is at the 11 mark, and I can estimate, step 3, estimate 1 beyond 11, so I can say 11.0. Here's another one over here. Now we have a 3 becoming a 4, so each of these is probably a tenth. So I'm reading that at the bottom of the meniscus, so that's this middle line here. And then step 2 takes the most kind of effort to try to decide what each line does for us. And so in this case, I'm thinking 3.5. And then step 3, you can read 1 beyond the line, 3.50. Now they're not all going to be 0.0. So here is 35, 36, 37, 38, 39. So this meniscus is in between two lines. So that's not a 0.0. 35, 36, but not quite 37. So what's between 36 and 37? 36.5. And again, some estimate with a 5. Some of us might think 36.4, 36.6, 36.7. We'd all agree on 36, and then 20 or so students would not necessarily disagree on the number 5, but you'll all be pretty close to number 5, 4, 5, or 6. We know it's not 36.9 or 36.1, so we'd all be pretty close to 36.5. Here's another one. And so 15, 16, 17, above the 17. This type of graduate cylinder doesn't have a meniscus. Plastic ones tend to have a much less meniscus than glass ones do. So this is a flat one, and so you can read that. And again, we can estimate 17.1, 17.2, 17.3. We can all kind of estimate that together and be pretty close to each other, and then estimate one place further. One other one is trying to get the volume of a irregular object. So the water fits in the graduated cylinder here. If this were a cube, you could do the length, width, height. If this were a sphere, there's a formula for that. A cylinder, there's a formula for that. But when it's an irregular object, what we do is something called water displacement. What water displacement allows us to do is just simply drop a solid into water and then get the measurement of the water before and afterwards, and then that difference would be the volume of this, in this case, hunk of gold. But even still, 15, 16, 17, 18, 19, almost 20, so probably 19.8 or 19.9. And again, we can estimate that 8. Here's another one. So again, you have to figure out the lines. I'll give you a moment to try it out. 25.9. 20, 1, 2, 3, 4, 5. Not quite 6, and so just shy of 26 is 25.9. And another one for you to practice with. This one's 63.5. And you'll see more of these in practice and eventually in lab as well. And so we have two types of units, what's called base units and derived units. Now, a base unit are limited to these 7: measurement, length, mass, temperature, time, amounts of substance, luminous intensity, and electric current. So these are what's known as the base units, and you can see the SI units, the International Standard Units. Most of them are metric, but just the system the rest of the world uses by default as this way we can compare with the same units. Again, most of these are going to be metric units as well. The one exception might be temperature. The metric unit for temperature is Celsius. The American unit, the empirical unit is Fahrenheit, but the SI unit is actually Kelvin, which we'll get to talk about Kelvin later in the year. So if you're not a base unit, then everything else is a derived unit. Notice volume is not on this list. A derived unit are things like area. We actually have to do a calculation in this case, length times width, or S times S. Well, if the length is a meter, what you end up with is meters times meters, and just like dimensional analysis, where you're trying to cross things out, you need a numerator and a denominator to cross things out. This doesn't cross out, they're both numerators, so you end up with an m squared. And so that's why this unit for area is m squared. And there's others, volume, frequency, and density. So volume is what we just talked about. It's m cubed. Well, why is it m cubed and not just milliliters or liters? Well, the volume of a cube is length times width times height. And again, if those units are meters, you get meters times meters times meters, which is meters cubed. And so we have the cubic centimeters and cubic meters, cubic feet. Those are the real units of volume. And then we made up a simile, a synonym for in terms of liters and milliliters and gallons. But the actual method of calculating volume is a length times width times height measurement and then calculation. We do have devices that can measure volume, like graduated cylinders, but it in itself, the volume itself, is actually a derived unit. And so you recognize these slides before. We have different sizes of cubes. This whole yellow cube here is just 1/1000th of this big cube here in terms of derived units. So here's the yellow cube, centimeters times centimeters times centimeters. We get this vocab of centimeters cubed. And again, by definition, that is also called, as a synonym, a milliliter. And a bigger cube, what is synonymous with 1 liter? If a centimeters cubed is a milliliter, then a liter is a decimeter cubed. A decimeter times a decimeter times a decimeter. So a liter of water would fill up this blue cube. And in fact, 1,000 yellow centimeters cubed would fit in 1 decimeter cubed, because 1,000 milliliters equals 1 liter. So here's kind of elaboration of volume again. Here's our length, width, height, which again is caused by length times width times height. Typically, we can certainly do this. You can buy a refrigerator. You can buy, actually, even cars. You can look up the cabin volume of how big the cabin is within a car, the refrigerators and dishwashers. We can get volumes like this, length, width, heights, but in terms of liquids, what we measure more so in chemistry lab is the amount of a substance. And when I say amount, I'm not counting particles, but I mean how much volume, how much space does it take up. And so a liter of water gets us kind of all of these values here. A liter of water is synonymous with equal to 1,000 milliliters, and it's also equal to 1 decimeter cubed. Now, talking about density, this is another derived unit. Density gives us pretty cool density columns with pictures like this, where everything kind of floats next to each other. Density is a derived unit. In fact, it's a derived unit from a derived unit. So the equation for density is mass divided by volume. And so volume is a derived unit, derived by doing a length, width times height calculations. Now again, you can measure volume directly using a graduated cylinder. You can certainly measure mass using an electronic balance. And when you divide those two, you get yourself a mass to volume ratio that we call density. Now the SI units for density is kilograms per meters cubed. We're not going to be using that unit much in chemistry, but what's kind of more common, especially in the context of water, is either grams per centimeters cubed, which is equal to grams per milliliters, because gram equals grams and a centimeter cubed equals a milliliter. So again, here's the equation, a bit more description about density. So it is a mass to volume ratio. It's what's called an intensive property, meaning it's always the same no matter how much you have. The density of a cup of water is the same as the density of a gallon of water. The mass will change between a cup and a gallon. The volume would change between a cup and a gallon. But that ratio of mass to volume is the same. And density, kind of by definition, is 1 gram per milliliter. It does change with salt water. It does change with temperature. It obviously changes with what state of matter it is there. But kind of liquid water at room temperature is 1 gram per milliliter. Typically, solids are more dense than liquids, which are always much more dense than gases. There's an exception to that, and again, water is being that exception. Water is one of the very few solids that actually expand a bit. So 10 grams of liquid water actually expands when it freezes. And when you expand, you increase the volume. Volume's in the denominator, so that actually decreases the density. And so solid ice, solid water is one of the few things that is actually more dense than the liquid phase. And so because of that, we can ice skate. Because of that, glaciers float. Because of that, quite a few things happen that would not happen otherwise. Now here's some numbers with density. Again, here we have 10-gram blocks of a few different substances, 3 elements in a compound. Here's the mass, they're all 10 grams, but notice the volumes are all different. And so when we do the calculation, mass divided by volume, we get different ratios here. So even though they all have the same mass and density aren't exactly the same. They are directly proportional to each other, because when the mass goes up, the density goes up, but the density itself is a ratio. And so this volume is changing because it only takes a little bit of lead to get the 10 grams. It takes quite a bit of lithium to get the 10 grams of lithium. And so lithium is a very low density material, lead is a very high dense material. And here you can see water is kind of the definition, the density of water being 1 gram per 1 centimeter. That's not a coincidence, that's how these scales came to be. So water could have a density of 1. But you can see that one of the misconceptions is that density is the same thing as mass. That's not true. It is directly proportional to mass, but it in itself is not the same. It's actually a mass to volume ratio. And this density would be true regardless of how many grams it is. If these gram numbers all went up, well, the volume would go up with it in order for the density to match. So we're going to do a quick calculation of doing grams divided by, in this case, centimeters cubed. And so you have the density equation where it's mass divided by volume. And so we can set up the expression here, mass divided by volume. That's not a negative sign, that's a bullet point. So here's the mass, 3.1 grams. Here's the volume, 0.35 centimeters cubed. That comes from this unit up here. And when you put this into your calculator, 3.1 divided by 0.35, couple of things. First of all, it is division, so you get 8.9. And beyond that, you get both units. Both units, if they're not crossing out, they both stay. And they can only cross out if they're the same. So here's grams, there's grams in the numerator. This slash line brings me a denominator, and that's where the centimeters cubed comes into play. So here's another example here. This one you can actually solve for the mass. So when you have 3 variables, density, mass, volume, we're going to give you 2 of those 3, and you can solve for the third one using your algebra skills. So in this case, the 2 variables we gave you is volume and density, and the third one that we did not give you is mass. And so if you have this equation, mass divided by volume, you can rearrange, in this case, multiply both sides by volume and get mass by itself. Since volume is in the denominator, if you were to multiply both sides, density and mass divided by volume, the 2 volumes would cross out and you'd end up with density times volume, which is what you see here. And then it's a matter of just plugging in the numbers. And so here's density, the 325 gram per centimeters cubed that was given to you. Here's the volume, which is the 25.7. Notice there's a little bit of a trick here, and we gave you mLs, but remember mLs is the same as centimeters cubed. This is not only looks like the algebra of plugging in the numbers after you made the variable, but it's also a bit of a dimensional analysis that the centimeters cubed crosses out, and you're left with just the grams left over. And so now you have grams over here. And again, in just like dimensional analysis, when you multiply numerators That is how to do dimensional analysis. Multiply the numerators and divide by the denominators. So 3.25 times 25.7 gives you 83.5 grams. So thank you so much for your time. Go ahead and practice this. And remember, chemistry is everywhere. And remember, you can reach out to me for some extra help. Thank you so much, everybody.